Good afternoon. This is Xu from Tsinghua University and the Supercomputer Center in Wuxi. Today, I will talk about our resource allocation optimization that has been deployed on world's third largest supercomputer. This work is collaborated with Shandong University, Qatar Computing Research Institute, and Emory University. Supercomputers are important high-end systems enable the computation of many large-scale science, engineering, and social problems. Those machines are known for their massive compute power, but none of them would be helpful without the I/O system to transfer input data and output results. On the cluster and supercomputers, the major I/O system is a parallel file system, a space made by many disk arrays, accessed through the storage nodes. Disk storage is usually much slower than the computation bandwidth, making I/O a potential performance bottleneck. Also, it becomes a contention point, as parallel file systems are shared by all computer nodes. In this work, we target a specific I/O architecture where a layer of folding nodes sit between computer and storage nodes. And this decouples the file I/O from computer nodes. Such I/O architecture has multiple advantages. First, it allows the compute nodes to adopt a lightweight OS by shipping I/O functions to folding nodes. Second, it reduces the number of connections to the storage layer. Third, this facilitates the connection between the two different network domains for computation and I/O. And finally, it provides an additional layer of prefetching and caching for better I/O performance. Due to those advantages, I/O forwarding is widely used among large supercomputers in the world. On this map, the red pins mark the 9 systems with I/O forwarding out of the top 20 machines at this moment. But I/O forwarding brings challenges as well. It's hard to provision forwarding resources at first. How can we know how many forwarding nodes to set up and how much total forwarding bandwidth is? The answer heavily depends on who will use this incoming machine, how much I/O they will do, how busy the machine will be, and how much money to spend on I/O. This is especially hard as centers have to design and buy hardware years before the machine is in production use, when people can gauge applications' actual performance and demand. Then, with a given forwarding architecture, it's also hard to manage forwarding resources at runtime. For a particular parallel job, how do we decide how many and which forwarding node to allocate? As a result, supercomputers mostly rely on resource over provisioning and adopts FFM, fixed forwarding mapping, so that we have static many-to-one mapping between compute and forwarding nodes. I will use, to give an example here, this is the architecture of Sunway TaihuLight in China, currently the number 3 supercomputer in the world. On the left, we have 40 cabinets, each containing a full 256 nodes supernodes. Together, they make over 40,000 computer nodes with over 10 million cores. Those computer nodes run the client side of LWFS, a lightweight user space file system based on cluster FS. On the right, we have 288 storage nodes forming the I/O backend. Running the Lustre servers, each storage node is a Lustre Object Storage Server, or OSS. Each pair of storage nodes are connected to a group of 6 object storage targets, OSTs, built on RAID 6 arrays. Together, they offer 10 petabytes space. In the middle, we have 240 forwarding nodes connecting the front end and the back end, running both LWFI server and last client. They are connected to the computer nodes through compute interconnection and to the storage nodes through storage interconnection, both high-speed InfiniBand network, but separated. Finally, we have two metadata servers. Here, FFM, which is fixed forwarding mapping, is set by connecting each 512 computer nodes, in other words, two super nodes, to a forwarding node. Remember, there are 160 super nodes, so FFM consumes only 80 of the available 240 forwarding nodes. This means that TaihuLight does over-provision forwarding resources when our intensive workloads need more forwarding nodes. System admins manually allocate them from reserved forwarding nodes. But FFM also leads several issues. First, there is no one-size-fits-all forwarding resource solution. Here are 10 large applications routinely running on TaihuLight. 9 of them are numerical simulations and 1 parallel graph engine. When it comes to I/O, they have all kinds of behavior. For example, Wolf and Cam has 1-to-1 L mode. AWP has N-to-1 mode. The rest has N-to-N mode. Those applications are bandwidth intensive. APT is LPS intensive, and DNDC is metadata intensive. Let me explain the L mode here at first. Here, N-to-N L mode is that each computer node accesses its private file in parallel. N-to-1 mode is that all computer nodes access a shared file. 1-to-1 mode means sequential I/O. We show an example here with 2 of those applications, the weather-focused application Wolf and the fluid dynamics code XCFD. We test with allocating them with different number of forwarding nodes. From 1 to 16, the y-axis shows L performance speedup compared to the baseline of using 1 forwarding node. Here, Wolf actually has a larger job scale, using 256 compute nodes. But as it uses 1-to-1 I/O, its aggregate I/O throughput stays the same no matter how many forwarding nodes you give it. XCFD, on the other hand, uses the more scalable N-to-N I/O mode, but benefits from more forwarding nodes through more than 4 doesn't seem to help either. With FFM, those applications are not going to receive customized treatment, and this Wolf job will receive twice the forwarding resource allocation as XCFD. The second problem with FFM is I/O interference, known as a major reason for inconsistent I/O performance. Each forwarding node is a potential contention point. With FFM, concurrent job sharing the same forwarding nodes may have conflicting I/O patterns and bring I/O interference. We show another example here with 3 applications mentioned before. This APT earthquake simulation, the Shen2 graph engine, and the LAMPS molecular dynamics simulation. We run them into 2 modes. First, with a dedicated forwarding node. With the 512-to-1 FFM ratio, here AWP and the LAMPS each runs on 256 computer nodes and gets allocated 1 forwarding node, while Shen2 runs on 1024 gets 2 forwarding nodes. Nobody is sharing forwarding nodes with others. The bars show the corresponding total L time in seconds. The second mode is what happens with FFM in production system, where different jobs need to share forwarding nodes. In this case, Shen2 gets 1 full forwarding node but has to share 2 forwarding nodes with its 2 neighbors. Compared to the dedicated mode, the shared mode causes a 4% I/O slowdown for AWP and 24 for LAMPS. Shen2 is hit much more heavily with its L time tripled. Interestingly, as we will see later, the interference mainly comes from only 1 node. between AWP and Shentu. This means for large jobs using thousands or more nodes, even if only one of its folding nodes is shared with an annoying neighbor, the entire job hurts all the same. Finally, with FFM, you are really unlucky when you got a slow folding node. Our data confirms a recent study on data centers where nodes suffer from fail slow. It means the nodes are still alive, but just very slow. Because they are functional, they are still assigned to serve computer nodes. And the users would have no idea what happened and just wonder why the L time is so long. This example shows read-write benchmarking results across 96 active folding nodes. While most folding nodes do report consistent bandwidth levels, a small number of them clearly exhibit performance anomalies. In particular, folding node number 8 and 34 are obvious outliers, working at only about 10% of normal performance. A job map to use such nodes will clearly suffer. In this work, we present an alternative approach to FFM called DFRA, which is dynamic forwarding resource allocation. The main idea is to upgrade a job's forwarding node allocation only when necessary. Imagine a hostel that may assign guests to share rooms. And the FFM, the policy is inflexible, one person, one bed. And the DFRA, the hostel will first look at the guest. If we have a normal traveler, we will keep the existing policy. If the guest has a lot of bags, we upgrade his allocation by giving him more room, meaning we give a job with high L demands more folding allocation. If the guest doesn't need space himself, but it's known to be disruptive to others, we also upgrade his allocation. We don't assign more folding nodes, but give him private folding nodes to provide isolation. So the key decision here is to judge what kind of behavior each application has. To this end, we rely on Beacon, a new end-to-end monitoring system to collect applications' history data and get their individual profiles. The basic assumption here is the parallel applications tend to have similar L behavior across many runs. Beacon itself is described in our sister paper, end-to-end L monitoring on a leading supercomputer. In this year's NSDI, unfortunately, the paper is just presented an hour ago. You are welcome to check out the paper, our open source monitoring software, and multi-level L monitoring data collection at this GitHub repo. With the help of Beacon, the first step of DFRA is to identify jobs that need more folding resources than granted by default FM strategy. To get a folding capacity upgrade, a job needs to pass several tests. At first, a job should have enough L volume and nodes performing I/O. In addition, we exclude applications that are metadata banned, judging by the average metadata request queue length as the forwarding nodes during L phases. Intuitively, more folding nodes cannot help applications bound by metadata request processing. For the jobs passing the test, we need to calculate the appropriate folding node number at first. This is done in a straightforward way. It's calculated by the number of computer nodes performing I/O times the maximum bandwidth per computer node, then divided by L bandwidth per folding node. And if the number of just folding nodes is greater than the actual folding nodes, we upgrade the folding node allocation accordingly. Otherwise, we keep the default mapping. Now we get to the second scenario of giving upgrades with folding resource allocation to identify jobs requiring dedicated folding nodes. This case is indeed much more complicated. First, to locate common sources of our performance interference, we conduct an interference study. Among 8 applications, with typical I/O patterns. 7 selected from the aforementioned real-world application, plus 1 widely used MPI I/O benchmark. We do pairwise co-execution among them. Each job uses 256 computer nodes under FFM. The 512 computer nodes running 2 applications will share 1 forwarding node. To gauge interference, we measure each application's overall I/O slowdown using its I/O performance in a solo run as a baseline. This table shows the pairwise slowdown measurement, and each pair of the number gives the slowdown factor of the application, listed as the row and column header respectively. For example, when DNDC co-runs with Shentu, DNDC is slowed down by 1.1 times, while Shentu 16.7 times. Both fonts highlight heavy interference with 3 times or higher slowdown. The first thing that attracts our attention is that the application AWP doesn't get along with anybody. This is the only application among that 8 uses the N21 mode, which is known to be very slow. And here, many computer nodes write down to the same file, bringing big synchronization overhead. What we found in this study is that notorious I/O mode is not only slow, but also highly disruptive. It can slow down the neighbor by up to 100 times. During to the laser synchronization, application using N21 mode will generate large numbers of requests, overwhelming request queues of forwarding thread pool, as shown here. Those requests are served at very low speed, exacerbating the congestion at the queues. Too bad for their neighbors. The second observation is that DNDC also introduced big slowdown to the most of his neighbors. The application accesses many small files, creating heavy metadata access load. Closer examination found that on TaihuLight forwarding nodes, metadata requests are given higher priority over normal file I/O to improve interactive user experience. This, coupled with the limited capacity of the laser metadata server, makes the metadata-heavy application and suspect bullies, because they often register very mild I/O intensity. Here we summarize the I/O interference root causes we have found, which are N21 I/O mode, metadata-heavy workloads, and high bandwidth workload, which I haven't time to present here, but you can see the paper for more details. High IOPS workloads usually together with small request size are easily become vectable. Then, to detect the I/O interference, we examine both this application and its potential neighbors. Those applications are the neighbors are the applications will share forwarding node with target under FFM. If either side belong to the above categories, we play safe and we give the target job dedicated forwarding node allocation. To summarize, here is the overall DFRA workflow. It works within the job scheduler, which examines every job upon its dispatch. It checks whether the job satisfies the 2 criteria for upgrades, whether it needs more or dedicated forwarding node. If any answer is yes, it calculates the number of forwarding nodes needed, allocates them from idle forwarding node pool, and remaps the job's compute nodes to their forwarding nodes. If there is not enough idle forwarding nodes, we allocate as many as possible. If both answers are no, we keep the default mapping. For all the forwarding nodes, we monitor their health and remove the few slow nodes from allocation. We implemented DFRA in C and Python by expanding the Slum job scheduler. All computer nodes are mapped to their default forwarding mapping using FFM. When a job is approved by DFRA for an upgrade, we abandon that FF allocation, and DFRA redirects its compute nodes to expand or dedicate folding nodes. This remapping is done at a per-job basis, and the remapped connections are removed at the end of job execution. Also, considering the abundance of the folding nodes in supercomputers, we choose to not perform downgrading. This could be changed. Sorry, something wrong with the projector. Is this? Is this? Okay, sorry. Hi. Okay. Okay, let's continue. Also, considering the abundance of folding nodes in this supercomputer, we choose not to perform downgrading. This could be changed in the future if necessary. DFRA has partially deployed on TaihuLight's production system since last year, February. Currently, users opt in by okay. Is it okay? Okay, let's continue. Okay, people opt in by including a parameter in job submission command. In the future, we plan to switch to the opt-out mode. When all job will go through DFRA unless specified by users. Also, DFRA is to be included in the parallel L system for the TaihuLight successor, which to be accepted to be extra scale. Such partial deployment allows us to evaluate DFRA in multiple ways. First, we examine the potential jobs that could be impacted by DFRA. We run the 18 months of L history data through DFRA decision making. On the pair of the pie charts, the blue slice indicates the portion of jobs that will receive upgrades from DFRA. For those denied upgrade, we categorize them by the first test failed during DFRA decision making. Here, the orange for the inefficient operations that cannot benefit from having more folding nodes. And And the pie on the left shows the split by job counts, which shows about 14% of jobs will qualify for DFRA. And the dominant reason of rejecting DFRA is the low L volume. That means 1 out of 7 jobs will benefit from DFRA. But when we examine the core hours consumed by those job categories, the story looks quite different. Those 14% upgrade jobs turn out to be heavy resource users, consuming a total of 80% of all core hours during monitoring period. This is understandable considering that large-scale production runs are more likely to be data-intensive. We then zoom into DFRA interference avoidance by running the pairwise slowdown experiments again. Here, we use different shades to mark the level of L interference. And the cell or the matrix give the slowdown factor or application at row header by the application at the column header. For example, the left top number 3.3 means an PIO test is slowed down by AWP 3.3 times. The NAP cells are filled with slowdown values. They indicate co-running pairs with interference dedicated by DFRA and then allocate expert folding resources. The left side gives the result under FFM and the right under DFRA. As expected, all the cases of significant I/O interference has been removed, and the highest I/O slowdown factor measured under DFRA is 1.1. So DFRA reduced the variability and improved the I/O performance at the I/O folding layer. Finally, we demonstrate the remapping overhead. How long does it take to do actual remapping? Here, the average remapping cost for different job sizes, together with the corresponding job dispatch time without remapping. It typically takes only a few extra seconds compared to the baseline. This minor delay is negligible compared to the total I/O saving. Since its deployment in February last year, DFRA has brought an average execution time saving of over 6 minutes. Using actual TaihuLight job history, we thus estimate DFRA overall resource saving at over 200 million core hours in past 8 months. To conclude, we come back to the challenge in provisioning and managing I/O forwarding on supercomputers. It's always hard to guess in advance how much resources a machine will need, and the resource demands also involve in a machine's lifetime. Our exploration on TaihuLight suggests that it seems the wise idea to over-provision overall forwarding resources and then give the low baseline allocation, considering that most jobs are not I/O intensive, leaving the majority of forwarding nodes available for flexibility on-demand allocation upgrades. This reduces resource wastage, improving both application performance and performance isolation, and provide additional fault tolerance against nodes with performance anomalies. Finally, our approach applies not only traditional I/O forwarding, but also provisioning and managing of shared boost buffer. And here's the talk. Thank you for your time.
We have plenty of time, so feel free to ask questions. I have one question to start with. So can application game your system? Because you are you have a policy that will add more nodes, forwarding nodes to applications that need them, right? So in one way, I could create an application knowing that you have that kind of policy, game the systems, and I will get more forwarding nodes, and I return my behavior to my basic behavior, but now I will perform much faster.
Yes, yes. This is the case. So we have the opt-in mode. User can specify whether to use DFRA because they often change the I/O behavior. But our history data shows that about 90% of the larger applications, they never change their I/O behavior.
Okay.
Yeah.
All right, so let's thank the speaker one more time.
Thank you.